All right. What we're going to do here in section 7 is going to continue to build off of all the stuff that we've done for the last couple sections. Section 4, 5, and 6, where we have been working a lot with factoring things, using synthetic division to factor, talking about a number of different theorems in terms of how we can find roots, and also discussing the fundamental theorem of algebra, where we get to the point where we can examine and identify all the roots that a particular polynomial equation has. Okay, we've been spending quite a bit of time focusing on how to relate equations to graphs, and in this particular section we're going to spend a lot more time focusing on the graphs of different polynomial functions. Alright, so we're going to use properties of end behavior, which you'll understand what end behavior means here in a little bit, to analyze, describe, and graph polynomial functions. Now, remember before, when we were doing all the fundamental theorem of algebra stuff, we kind of used a graphing calculator and the graph itself to kind of, I don't want to say cheat, but really that's kind of what we were doing to help us zero in on where some of those real number zeros might be to make our process a little bit smoother. Okay. In this section here, what I am going to make you do is on a quiz or a test at least one time is you're going to have to graph something without the use of a graphing calculator. So that means finding zeros based on the rational root theorem, guessing and checking with synthetic division to figure out which of those actually work, and moving forward from there. So it's going to take a little bit of time to do that, all right? But it's one of those things where you're only going to have to do one of them. Okay, and then we're going to talk a little bit about maxima and minima of polynomial functions to solve problems, and what that actually means throughout the context of what we're trying to do here. So there are going to be a number of terms that we discuss in here that are going to be important for you to understand. First, we're going to talk about end behavior, or more or less, what does the end of your graph do as it approaches really, really large or really, really small values of x. Okay, a turning point is more or less what you would expect a turning point to be. Okay, where does your graph turn and begin to head in the opposite direction that it was originally headed in? And then a local maxima and local minimum just mean, do we have a maximum point or a minimum point as the result of a turning point in a graph? Okay, so if your graph is headed down and then it turns back up, the point at the bottom of that, the turning point at the bottom of that, would be a local minimum. If your graph is originally increasing and heading up and then turns and starts decreasing and heading back down, that point is now going to be a local maximum. All right, and it is possible to have more than one local maximum or more than one local minimum for a particular function. Okay, now before we get into this a little bit, hopefully this section won't be as long and kind of drawn out as some of the last ones have been. But again, I encourage you to sit here and maybe try to think about some of the stuff in like 10 to 15 minute segments if you want to. So look at some stuff, when we get to the example 1 stuff, once we get through that stuff, go ahead and take a look at your homework a little bit and see if you can apply what the video said to the stuff from example 1. And then come back, take a break, come back, then start looking at some of the example 2 stuff. 10 to 15 minutes, look at it, pay attention, take some notes, then go ahead and take a look at your homework. Okay, and then take a break. It doesn't all have to be done in one sitting, and that's one of the valuable parts of being able to do things this way. All right, is you have the opportunity to see stuff ahead of time, but you also have the opportunity to break things up and kind of find out what works best for how you want to try to approach this stuff. All right, so if you look at this particular slide that's up here, we're going to start examining a little bit more the different polynomial functions. Now, over here on the left, when we have first degree or linear functions and second degree quadratic functions, all right, those are things that we should be familiar with the graphs of those, because we've graphed all of those before in class. Okay, taking something that's in y equals mx plus b form and being able to graph it on a coordinate plane. Okay, here I'm taking something, a function, ax squared plus bx plus c, and being able to graph it on the coordinate plane. Okay, finding the vertex point, axis of symmetry, y-intercepts, all that stuff, being able to graph it. The ones that we haven't discussed a whole lot are going to be cubic functions, where you have something where it's x to the third, or a third degree. Quartic functions, where we have something that's a fourth degree. And quintic functions, where we have something that's a fifth degree. Okay? Now, obviously, as you start manipulating things with those functions, they're not going to always look exactly like this, or exactly like this, or exactly like this, but they're going to maintain the same general shape. Okay, so what we're going to talk about, primarily is when we start getting those degrees that are more than 2, how can we figure out or examine what the graph is going to look like without actually having to graph it on a calculator. Okay, so the first thing we're going to talk about in reference to that is end behavior. Okay, and more or less what we're talking about with end behavior is like I talked about at the very beginning. Okay, when we're analyzing end behavior, we're taking a look at both ends of the graph, or as x values approach infinity, positive infinity. Now this is an infinity sign, it looks like a sideways 8. All right, or as they approach negative infinity. Okay, so if you're looking at a coordinate plane, okay, x values going this way, as we get way off to the right, would be approaching positive infinity. We go the other direction. As we keep going in a negative direction, eventually we're going to get really large negative values. Okay, and we want to see what's our graph going to do as our x values approach that. Okay, now the degree and the leading coefficient, in terms of whether it's positive or negative, are going to be very important in helping us figure out what end behavior is for these particular functions. Okay, so if you understand, how a cubic function works, how a quartic function works, and a quintic function works, and what negatives have the ability to do to those, it's going to help us figure out what the ends of these graphs are actually going to do. Now, this is a very important slide here because it basically kind of summarizes how all polynomial functions are going to behave on their ends. Okay, so what we're first going to look at up here is, the key is, our leading coefficient is greater than 0. And all we mean by greater than 0 is basically our leading coefficient is going to be positive. Okay, if it's a positive and we have an odd degree, meaning we have like an x to the third or an x to the fifth. Okay, if our leading coefficient is positive, we always read graphs from left to right. So as I start looking at this graph coming from this direction, okay, I know the tail looks like it's going down, but really as my x values increase, right, my function is actually increasing. It's going up and up and up, and it goes that way. And obviously it widens out as it goes that way. So what we'd be looking at here is, as x approaches positive infinity, or as we move this way, okay, my graph continues to go up. All right, so the function itself, like it says right here, approaches positive infinity as well. Okay, or it's going to continue on towards really large values. Now, on the other hand, if we start looking at the function moving this way, okay, as my x values get more and more negative, my function itself continues to go down. So as x approaches negative infinity, the function itself also approaches negative infinity. Okay, so basically what we're looking at here is, as my graph, the x values for my graph start to approach infinity or negative infinity, where do the y values of my graph go? Do they go up towards positive infinity, or do they go down towards negative infinity? Okay, if you look down here, if we would have a negative coefficient, the only thing that changes is our graph pretty much flip-flops. Okay, we begin with something that's decreasing going down, and it continues to go down in that direction. Okay, so in this case, as we approach negative infinity, the graph itself goes up towards infinity. If we go this way, as we approach positive infinity in terms of an x value, my graph goes down towards negative infinity. All right, so it's a simple concept, but it takes a little bit of understanding, because you just have to think about infinity as just being very large values, or negative infinity being very small very large negative values. Okay, so that's how it works for odd degrees. Even degrees, we saw a little bit of this when we were dealing with quadratics, where we had parabolas. If it's positive, you're going to get some type of bowl shape similar to what's drawn up here. If it's, to the second power, it will be a parabola. If it's to the fourth power, it's going to resemble a parabola, but it might have some, kind of bumps in the middle. It might look more of a W shape, but we're not really worried about what it does in the middle. We're more concerned about what it does on the ends. Okay? So if you look at it in this sense, as our x values approach positive infinity, the graph itself is going up. So it would be approaching positive infinity. As we approach negative infinity in terms of x, it's still going up, so the function itself would approach positive infinity as well. Just vice versa when you have a negative leading coefficient down here. Okay, now as I approach positive infinity, my graph is going down, so as I approach positive infinity, the function is approaching negative infinity, or the y values are approaching negative infinity. As my x values go this way, all right, my graph is still going down, so that means it is also approaching negative infinity. Okay, so just something to think about. Again, as we approach different x values, where's our graph going in terms of up and down? All right, now the whole key to doing this is being able to do it without having to look at an actual graph of something. Okay, understanding what a quartic is, what happens if you have a negative leading coefficient, understanding what a quintic is. All right, and what happens if you have a positive leading coefficient. So we'll start with A here. Okay, the key I'm looking at here is the power and the leading coefficient. So it's fourth and it's negative. So that means I'm going to have something that looks like this. Now again, in the middle here, it could vary as far as having some bumps or lumps in there. All right, but for right now, we're just worried about the ends of it. So as x approaches positive infinity, the graph itself, which in this case, or the function itself, which is q of x, okay, so as we go this way, the graph is going down, all right, so it would be approaching negative infinity. Okay, if we look at it from the other direction, as x goes towards negative infinity, the function itself, or the y values of the function, are still going down, so they would also be approaching negative infinity. So that's all we're really looking for right there when we talk about end behavior. Okay, as we go way out for increasingly large values of x or increasingly negative large values of x, all right, what is the graph doing? Okay, if we look on the bottom here, all right, I'm worried about the degree and the leading coefficient. It's positive and it's odd. So that means I'm probably going to be going up or something like that. As I move to the right, my entire graph is increasing. Now again, there could be some lumps or bumps in the middle of that distort the inside view, okay, or the view in this area. But again, the ends of it, where do they go? So again, as x is going to approach positive infinity, what is the function itself going to approach? Okay, well, as we move towards positive infinity, the graph is going up, so it is also approaching positive infinity. As our x values go in the other direction, what is our function going to do? Well, as I start moving this way, my graph is going down, so it's approaching negative infinity. So again, when we're talking about end behavior, okay, that's all we're really looking at. Okay, so what is the degree? What is the leading coefficient? And what are the ends of this graph going to do? Or what are they going to be? Okay, now if we move to something like this where we actually have a picture of a graph, okay, identify whether the function graph has an odd or an even degree and a positive or negative leading coefficient. Okay, well, the first kind of little hint with this is look at your ends. If they're headed in the same direction, like say they're both pointing up or they're both pointing down, that means you're going to have an even degree. Okay, if they're pointing in opposite directions, okay, like is the case right here, one's going up, one's going down, that means that we're going to have an odd degree. So I can write that down right away. I know it's going to be odd. Okay, now the question is the leading coefficient, which we referred to on the other one as just an A, okay, is your A, or leading coefficient, greater than 0 or less than 0? Or is it positive or negative? Well, when it's an even degree, it's really easy because if your bowl or your ends face down, that means it's negative. If your bowl or your ends of your graph face up, that means it's positive. Okay, so even ones are a lot easier. With negative ones, what you're looking at is when we're starting right here, or at least the part you can see on your graph, as I start looking this way, as I move that way, what's it doing? Well, in this case, it's decreasing. It's going down. Okay? So if it starts by going down, or it's decreasing, that means that my leading coefficient has to be negative, okay, or less than 0. All right, so in this case, it is an odd degree. The graph begins by decreasing as we start moving in a positive direction. So that means the leading coefficient has to be negative. Now, in this case here, you're probably looking at something that would be like a quintic or an x to the 5th function. All right, now, why don't you take a look at this one here a little bit and think about it in the same way we just looked at the last one. So pause, take a look, see what you come up as far as with a degree and a leading coefficient. Okay, now as far as the degree is concerned, again, we want to look at our ends to begin with. Which direction are they headed in? Are they going in the same direction or are they going in opposite directions? Well, in this case, they're going in the same, so that tells me that I have an even degree. Okay, even degree because they're both headed in the same direction. Now, as far as is it positive or negative? Okay, we said with even degrees, if it's positive, you're bowl-shaped. Okay, and I know this doesn't necessarily look exactly like a bowl, like a parabola did before, but if a parabola was pointing up, all right, that meant that it was a positive leading coefficient. The same applies here. Now that we know it's even and both ends are pointing up, that means that my leading coefficient has to be greater than 0 or it's positive. Okay? Had the thing opened the other direction and been down like this, that would have meant that our leading coefficient was negative. Okay? So once you get a little bit more familiar with how something like that's going to work, all right, as far as the difference between the evens and the odds, how they open up and down, so on and so forth, it becomes much easier to answer these questions. All right, here's another example, just real quick. We're going to have something that has an odd degree because our ends are going in opposite directions. And if you look at this, as we read the graph from left to right, my graph is decreasing. Okay, so what that means is I have a negative leading coefficient. Okay, or A, as they referred to earlier, is less than 0. Okay, and that would probably be something that's in that x to the 3rd range again. Okay, here we have something that resembles like a W or kind of a bowl again. Okay, they're both pointing up, which means I'm even. Okay, it's one of those things where the bowl is pointing up, not down, so that means we have a positive leading coefficient. Okay, or A is going to be greater than 0. Okay, so nothing too terribly difficult about those right there as long as you remember what's going on there. Again, had this opened down, say it had been the same thing but opening down, it's still even because those ends are pointed in the same direction. They're both going towards negative infinity. All right, but because the bowl goes down, that would mean we'd have a negative leading coefficient. All right, now we're to the point where I talked about this a little bit at the beginning, the very beginning of the video. And at this point here, if you feel like you need a little bit of break, we're about 18 minutes in. You could probably take a look at your homework and see what problems correspond to the stuff that we've already talked about, and then come back to this part, because this part is going to take, I only got one of these problems up here, but it is going to take a little bit of time. Okay, basically what we're doing is kind of applying some of the stuff that we've done over the past few sections, putting it all into one, and to be able to sketch a graph here. Okay, so here's the deal with how this is going to work. Okay, what we're going to have to do is we're going to have to find as many zeros as we can possibly find that are real numbers. Okay, so using synthetic division and stuff like that. We will first have to use the rational root theorem to figure out what my possible zeros are, and then you're going to have to guess and check a little bit as far as which numbers you fill in. All right, you're going to use your y-intercept, which the y-intercept for this works the same way it did for quadratics. It's always just the last number that happens to be up there when things are written in standard form, or it's your constant. Okay, then once we figure out where our zeros are, we compare it to the degree of our particular function. We think about end behavior and all that stuff. And then we have to find some points in between that we can put into a table or something like that, so we can get a better idea exactly what the graph is going to look like. Now, the thing about this is sometimes it's really, really tough to be able to get an exact picture of these graphs, just because there tends to be a lot going on sometimes. So we just try to do the best we can, and then we compare it to a picture of the graph at the very end. So you'll want to make sure that you write down all this stuff that's written on this particular chart, so you know step by step how this is supposed to work. Alright, so the first thing I'm going to note about this up here is that my leading coefficient is greater than 0. Okay, it's third degree. Alright, so my guess would be I am going to have something that looks similar to that as far as my graph goes. Okay, it might vary a little bit in between. Maybe it looks a little bit more like this. Alright, it has a few more bends in there. Alright, but that's what we're looking at as far as just understanding leading coefficient and degree, how they affect what's going on. Okay, and in this case, as far as my end behavior is concerned, as I'm going towards negative infinity, the graph is also going towards negative infinity. As I go this way, regardless of which type of graph I have there, the specifics of it, it would also be going towards positive infinity. So that's just kind of applying some of those concepts we talked about earlier. Now I have to use the rational root theorem here. Alright, I want to think about what are my factors of p, which would be this back here, which that number also serves as our y-intercept. Okay, and what are my factors of q, which would be my leading coefficient right here. So factors of 6 would be 1, 2, 3, and 6, and my factors of q would be 1. Now this is like a lot of the examples we did in class. Because q is just 1, usually, to find your possible roots, you take p and divide it by q. Well, here we don't really have to do that, because p divided by q is just going to give us whatever all these p values are. So those are all my possible roots that I can have. Now here's the part where before we graph things ahead of time to try to narrow down which of those roots would actually work based on what we can see in the graph. Well, here I'm asking you to graph things longhand without looking at the graph of something until the very, very end. So we're going to kind of have to guess and check a little bit as far as what values we want to use with synthetic division here. So I'm just going to start with something relatively easy. So I think I'm just going to start with a 1. Now again, this is a guess. If it happens to work out, great, and I get a remainder of 0. If it doesn't work, that means I'm going to have to go back and pick another value and go from there. Okay, so hopefully, if I fill all my coefficients in here, 4, 1, negative 6, this will work because it'll save me a lot of time. Okay, so 1, 1, 5, 5, 6, and 6. Alright, so remainder of 0. I got lucky there. Okay, so what that's telling me is 1, okay, I'll write that up here, x equals 1 is a root of this. Alright, now, as far as the rest of this is concerned, that means what I have left over, first of all, it would mean x minus 1 is a factor, and then what I would have left over would be all this stuff down here. Alright, which gives me x squared, because we drop a degree. Alright, we drop a degree, plus 5x plus 6. Now I want to look long and hard at this part, because hopefully I can just factor what's inside of here, alright, which it looks like I can. X plus 5 and 1. Alright, so what that's telling me is x equals negative 5 and x equals negative 1 would be my other two real number roots that I can have with this. Okay, now, had you not been able to factor this, alright, maybe you would have had to go ahead and try to do synthetic division again. But most times I think what's going to happen is, most of your roots with these are probably going to be real. So you should be able to factor that part. If we couldn't factor it, that probably means that we have imaginary roots, and those aren't going to help you as far as graphing this goes anyway. Okay, so what we'd be looking at so far or right now, is at least I know where my roots are supposed to be. Okay, so if I start kind of making a graph here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. I'll go further that way. 2, 3, 4, 5, 6, 7. I'll extend a little bit here, I think. Okay, now what this is telling me is -1, -5, so 2, 3, 4, 5. Oops, wrong spot. Should have been right here. Okay, and 1 are roots. So let me pull up my eraser quick here so I can get rid of this one that's in the wrong spot. Oh, erase the whole line, but that's okay. Alright, now that I have that out of there, get my cursor back here. Okay, and I have all those roots in the correct spot. I'll draw my axis back in there a little better. Okay, I know my graph is going to intersect those points, okay, or intersect at the x-axis in those spots. Okay, I do know, again, that my function, if I look up here, is going to take on that type of look here. Okay, the problem is we're not necessarily 100% sure where exactly it's going to bend and where it's going to turn. Okay, so like I said, I know if I have all this on my graph, kind of drew some dots in there a little bit. Okay, I know it's probably going to take on something similar to that, but what I need to go ahead and take a look at is like up here where it starts to bend a little bit. I need to be more specific about where exactly that's going to work. So what we do here is we just start picking values of x and filling them in to our original equation and try to get a little bit better idea of what those bends and breaks are going to look like. Now, the other thing I can think about here is go back, my y-intercept, okay, is -6. So if I go down 1, 2, 3, 4, 5, 6, okay, I know for sure that my graph is going to go all the way down to that and come back up. So that part I can be sure of right now. So that's why I put it in solid. So I want to pick something probably between -1 and -5, so probably -3. Maybe fill that in to that equation. So if I look for f of -3, okay, I'd be looking at -3 to the third plus 4 times -3 squared plus -3 minus 6. Okay, so I'm filling in -3. I'll write this over here. And I want to see what I'm going to get out of that. So -3 to the third is going to give me -27 minus, looks like I'm going to get, well, actually that's going to end up being a plus here because -3 squared would give me 9 times 4 would be plus 36. I'd go -3, then -6. So -27. If I go minus another 3 would get me to, did I do something wrong here? Let's see. Because if I go negative, $9.36, would I get 0? That doesn't make a whole lot of sense here. Because if I go -3 to the third gives me -27. Okay, because 3 times 3 is 9, times 3 is 27. It's going to be negative. Okay, the 4 in here, so -3 squared would be 9. 9 times 4 is 36, so I'm okay there. Okay, -3, or plus a -3, minus 6. Okay, so the problem I'm running into here is -27 minus 3 would give me -30, minus 6 would give me -36, so I'd end up getting 0 out of this. All right, so if I put in -3, I get 0. Let's see here, 5, 5, 6. Interesting. Did I? Oh, I did. Hopefully somebody caught that in there. I factored wrong in here. Okay? To get 5, I don't do 5 and 1. It should have been 2, and it should have been 3. All right, which would have changed my roots. I would have had -2 and -3 as my roots instead. All right, so you can see as you go through this how little things like that make a big difference. So let's go back here a second, and I'm going to just kind of clear out. So hopefully if you have anything up here that you want to rewrite down here for a second, go ahead, and then I'm going to erase everything and kind of start over. So we know our roots are 1, -2, and -3 after doing that and actually getting this part factored correctly. Okay, so what I'm going to do here is I'm going to erase all the ink on here, and I'm going to go with what we just talked about. So my roots are 1, -2, and -3. Okay, so again, you can kind of see how easy it is to get off a little bit if you don't factor correctly. So now let's go back to my graph here I was trying to make. 3, 4, 5, 6. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so now that I have this straightened out a little bit, 1, -2, and -3 would be my roots. So again, we're looking at a graph that's probably going to be something along those lines. Now again, my y-intercept is -6, so 1, 2, 3, 4, 5, 6. So again, we'd probably be down here a little bit lower. So this part I can be a little more sure of that it's going to go like that. Okay, so now I'd want to pick some other values, and right here, because these two are right next to each other, you can't assume that it's going to go a whole lot higher, so we could probably fill that in. Okay, and over here, maybe we'd want to pick one value to the right of that, so maybe we pick f of 2. All right, and see what happens. We do that. 2 to the third plus 4 times 2 squared plus 2 minus 6. Okay, so again, we're just picking random x values to try to get a better idea what this graph is going to look like. So that's going to give me 8 plus 16 plus 2 minus 6. So you can see how we're going to end up with a pretty big value there when we fill in 2. All right, so 8, 24, 26 minus that can be 20. So that means at 2 right here, I'm going to be way, way up off the charts. All right, so when we go through that, you know, we know that that end is going to go way, way up there. And I would assume you're going to get something similar if you come down here. Now, a good rule of thumb when you're doing this is after you figure out your roots and your y-intercept, you know, you should probably pick 2 or 3 other points, two or three other key points throughout the rest of the graph that you think are going to help, you know, solidify what your graph is actually supposed to look like. So again, I apologize for not getting that factored correctly in the first place and making things a little bit harder than they needed to be. Okay, but that's kind of what happens with math. Sometimes you're right, sometimes you're wrong, and you got to go back and check to see what is and isn't working. Okay, now this gives you a much better description of what the real graph would look like, and we were close. You can see how your end behavior here, these things are probably really going to start to go up, probably to the point where you might not necessarily be able to get anything else on your graph. You can see in here, say you would have filled in like -2.5. It doesn't necessarily look like you would have got a whole number out of that either. So that's the other thing that becomes a little bit more of a factor as we start going through some of this stuff. All right, we did talk about turning points a little bit, one way here or there. Turning points, again, if you look at the graph that we just had previous to this, we have 2 turning points. We have one here and we have one here. Now the thing that we want to do with turning points is we want to figure out the point at which it actually turns, okay, or the value, the y value at which it actually turns. Is it a maximum or a minimum? Okay, well, in this case here, because we were increasing and then decreasing on the other side, this would be what's referred to as a local maximum. And down here, we're decreasing, and then we hit it, and then we turn back up and start increasing, so this would be a local minimum. Now, the reason we call them local is because we're just looking at what is happening with the graph around them. Okay, they couldn't be like absolute maximums or absolute minimums, because you see this graph continues to go up and this one continues to go down. So there's obviously other points or other values, y values on this graph that would be smaller or greater than they are. Okay, but in this particular situation, there's still a maximum or minimum compared to everything that's going on around them. All right, and that's more or less what this slide was trying to tell you. Okay, I just tried to use a little bit simpler terms to make that work. Okay, this is just something you should probably read through. A polynomial function of degree n has at most n minus 1 turning points and at most n x-intercepts. Now that's what we talked about with the fundamental theorem of algebra. Okay, more or less think about it this way. If I start with a degree of 4, okay, what this is saying is that would make n 4. If I start with 4, okay, what that means is I can have at most n minus 1, so basically 4 minus 1 giving me 3. I can have at most 3 turning points, and I can have at most n x-intercepts, or basically what it means is n roots. So in this case, I can have at most 4 roots. Well, that was the entire point of the fundamental theorem of algebra, figuring out how many roots that I can actually have. Now remember, when we're talking about x-intercepts or real roots, just because my degree would happen to be 4 doesn't mean I have to have 4 real roots. There could be imaginary ones embedded in there somewhere. All right, but just know you have the possibility of having 4 real roots. Okay. Again, this down here is just saying it has n distinct roots. All right, meaning the total number of roots will add up to whatever your degree is. Okay. Then, as far as what we're going to do with maximum minimums, we can state just by looking at something whether it's a maximum or a minimum. If you wanted to be more specific about the maximum and minimums, like what the actual y value is there, we'd probably use a graphing calculator. So I just put this stuff up here to give you something to look at so you could reference. This walks you through step by step how you can find maximum or minimums on your graphing calculator. This will be something that we're going to focus a little bit more on in class, but the steps here do apply to how it would work on your calculator. Okay, so if you want to pause and take a look at some of this stuff as you go through, they give you actual examples of how this is supposed to work. All right, we just continue it on to the next slide. Again, what you're looking for when you're finding, your local maximum, or this down here would be a local minimum, is, okay, what x value are we looking at that gives us the y value that would actually happen to be your maximum? Okay, or down here, what x value, all right, gives you the y value that happens to be a minimum in this case. And you can see how they zero in on this down here. The 1.7 for the x gives me the negative 19.7 that happens to be my local minimum in this case. Okay, so really that's all that I wanted to get out of this. If there's some story problems or stuff, we'll probably talk about that a little bit in class. All right, again, I apologize for kind of mixing up that whole graphing thing. Hopefully you still got the gist of what was going on, because I made corrections as I went through that. Now you can see how we're taking everything that we've done previous to this and really trying to apply it and understand how all this stuff is supposed to work as far as all the concepts that we've talked about to this point. All right, so if you have questions, again, you have to make sure you ask. There's more than enough information in the video to get you started on your homework. Okay, so make sure you take all these concepts and keys and apply them to what it is that you're supposed to have done.